All right, so we're going to do some Lewis dot structures and a little bit of review before we get started on those drawings. Okay, so we have ionic and covalent bonds. Those are your intramolecular forces. They're holding those molecules together. Ionic bonds are formed by electron transfer. So we have cations and anions, and then they have electrostatic forces holding them together. Opposites attract. How do we know if something's going to be a cation or an anion? So the cations have low ionization energy. So I'm going to take calcium here. Calcium is in group 2. He has 2 valence electrons. So I'm just drawing the electrons on the outermost level, the valence electrons. And he wants to become like a noble gas. He can either add 1, 2, 3, 4, 5, 6 electrons to have an octet like a noble gas, or he could just lose those 2 electrons. Well, he has low ionization energy, which means it costs just a little bit of energy to get rid of those electrons. So he's going to get rid of those 2 so that he now has a positive 2 charge. He has 2 extra protons, and electrons are negative. So he has 2 extra positives, then he's going to have a 2 plus for its charge. And he is now going to go down to his lower ring number. So calcium here is in ring 4. So now he's just going to have 3 full rings and pretend he's a noble gas. Whose noble gas is he going to pretend like? Argon. So he's isoelectronic to argon. He forms cations. He's in group 2. It's easier to get rid of those. How about chlorine? Chlorine has 7 valence electrons. And again, I'm only drawing the electrons on the outer level, the valence electrons. He is missing 1. So he could either remove all 7 or add 1. And I look, and he has a high ionization energy. So it'd take a whole heck of a lot to lose all 7 of those versus adding 1. If he adds 1, he has that 1 extra negative. 1 extra negative, and so that is his charge. And so that is how he is an anion. These 2 guys can now interact with a fixed ratio, which we'll talk about on the next slide, to form an ionic bond. Whereas the covalent bonds are about sharing electrons. You can share them equally and be nonpolar, or you can share them unequally and be polar. So intramolecular forces inside the molecule. Intermolecular forces are holding different molecules together. So we look at our intermolecular forces when we're looking at things like solubility and surface tension, because that's holding multiple molecules together. We look at both of them to look at some other physical properties like boiling point and melting point. So ionic bonds typically have higher melting and boiling point because their intramolecular forces are stronger, but they also have intermolecular forces that affect that as well. Okay. So let's draw ones just so we can visualize what we talked about earlier. Magnesium chloride. Do not assume that that is just one magnesium and one chlorine. Why? Magnesium is a metal and positively charged when it becomes an ion, and chlorine is negatively charged. Magnesium has a 2 plus charge. Chlorine has a 1 minus charge. So what you've been doing to find the formula the whole time is crisscrossing. So that formula, MgCl2, 1 magnesium is with 2 chlorines. That is the fixed ratio that every magnesium and chlorine compound has. Why is that? Because magnesium has 2 positives, so it takes 2 minus 1 chlorines for them to balance out to be that neutral compound. That is why the crisscross works. But now we're going to show it in a drawing form. Magnesium, 2 valence electrons. Chlorine, how many chlorines? 2 chlorines. Each chlorine is in group 17, so it has 7 valence electrons and 1 open spot. Magnesium is in group 2, so it has 2 valence electrons. So you can use the groups to figure out how many valence electrons. And maybe when you draw it like this, you might start to notice magnesium wants to lose 2 electrons to become a cation. This 1 electron here can go and be deposited in that chlorine. The second electron can be deposited in the second chlorine. So all those electrons could go to one other element, multiple other elements, one atom of that element, multiple atoms. This is the electron transfer. And then magnesium ends up with brackets being a 2+, and chlorine, 2 of them with brackets, ends up being a 1-. So this is showing what's going on here. For the chlorine, we're going to show him with all 8. Magnesium, I'm showing him with none, but technically there's just none in row 3, but it's full in row 2. So that is how ionics deal with drawing their structures. They don't have a specific shape, but covalents have a specific shape, and we're going to get a little bit into that today. Boron trihydride, find the center atom. Okay, normally it's the one that's also the most symmetric. So if you don't have an electronegativity list, or you don't remember the trends where the electronegativity goes up and to the left, so you want somebody that's furthest lowest and to the left, or up and to the right, sorry, I think I said up and to the left. You want the least electronegativity, so you want the one that's lowest and the most left. If you don't have that, just remember it's symmetric. So boron's going to go in the center. Hydrogens are going to go around the outside. Boron, group 13, 3 valence electrons. Hydrogen, group 1, 1 valence electron. Hydrogen and boron are both weird. So hydrogen maxes out at 2. So he actually only has 1 gap. Why? Because helium, 1s2, helium only has 2 electrons. So hydrogen can't have 8 because he can't go past helium. He just wants to be like helium. So hydrogen has 1 electron and 1 gap. The gap is telling you the number of bonds. So 1 gap, he can do 1 bond. Boron is also weird. He has 3 electrons, but he doesn't want 8 either. He just wants 1 bond per each electron. So his max is 6. Okay, so he can do 3 bonds because he has 3 gaps. Well, that works out kind of perfectly, right? Hydrogens can only do 1 bond, and boron can do 3. So when I look at boron, I see he has 3 bonds. When I look at hydrogen, each hydrogen has 1 bond. You do not bond on the outside. It's like spokes on a wheel. Okay? So this is telling me that boron has 3 bonds and hydrogen has 1 bond each. How many electrons is that? So a single bond has 2 electrons in it. So you're not going to see it like this on a test anywhere, but I call these the dumbbells to draw in. It's making sure we get the right total. So boron has 3 electrons from its valence, 4, 5, 6. That's what he was supposed to max at. He was supposed to fill in 4, 5, 6, and he did. And now we go look at hydrogen. Hydrogen has 1 valence electron, and he needed to fill 1 gap, 4, 2. And that's what he needed. So this is my total structure of boron trihydride. How else could you do it? You can use it the same way we do molar mass. 1 boron and 3 hydrogens is equal to the valence electrons of the bond. Boron has 3, hydrogen has 1. 1 times 3 plus 3 times 1 equals the total number of valence electrons. So I should have 6 electrons here. Now, when you do the SOL, sometimes they show these without bonds, and they show them as 2 dots next to each other. Okay? Whenever those 2 dots are next to each other, that also signifies a single bond. And they do that in there because they notice a lot of people tend to forget that those bars mean 2 electrons, but really the better way to draw this is with the bars, so you clearly see it was a single bond that was connecting each of those structures. So this is its general shape that it would have. And we'll go more into that again, like in another video. You can always hit pause, try to draw them on your own. Boron with 3 fluorines. Fluorine, 1, 2, 3, 4, 5, 6, 7 valence electrons, so he's missing 1. So he also only wants a single bond. What's different about this guy? We have 1 boron and 3 fluorines to get our valence electrons. 1 times 3 plus 3 times 7 is 24. So this is not our finished structure. When I draw in these guys, boron's done. He has 3 valence electrons and he's filled in the other 3 gaps. So he has an octet of 6. His is just incomplete because he doesn't need 8. Fluorine here would be marked completely wrong if you left it like we did for hydrogen. Why? Because I'm only showing 1 valence electron for fluorine. I only show the electrons that are on their side of the bond. Fluorine is supposed to have 7 valence electrons. So the actual completed structure is more like this. Still boron with 3 bonds, but we make sure we show all the electrons on the fluorines. And again, if you wanted, you could draw them like this. And some people draw them with the X's for the center, so you can see which ones came from boron and which ones he's sharing. But again, you see boron has 6 there. NH3, nitrogen goes in the center, hydrogen goes on the outside. Hydrogen's a single bonder. How many is nitrogen? Nitrogen's in group 15. So he has 5 valence electrons. So he has 3 gaps. So he wants 3 bonds. And lo and behold, he has 3 bonds here. This is not complete. My hydrogens are complete. They have 1 valence electron for each one. And then they are sharing to make 2 for their octet. Let me rewrite this over here so you remember. Hydrogens max at 2, borons max at 6 for the octet. There's one other rule that we're going to get to, but pretty much everybody else maxes at 8. But those are your starting rules right there. Look at nitrogen. Nitrogen is only showing 1, 2, 3 valence electrons. How many is supposed to have? 5. Make sure you check at the end that the valence is correct and the octet is correct. So nitrogen has 5 valence now, and then 6, 7, 8. So that is our completed structure of ammonia or nitrogen trihydride. How about this guy? Least electronegative in the center. Fluorines out here, hydrogens there. You could have mixed up your fluorines and your hydrogens on any of those spots. That is fine as long as nitrogen's in the center. Both of those are single bonds. That's why I gave them single bonds. Same thing as before. Nitrogen has 1, 2, 3 valence electrons in the 3 bonds, but he needs 5 total. Same thing as before. Fluorine is only showing 1 valence electron. Make sure you show him with his 7 valence electrons. So those are the completed structures. So these guys look very much the same, but boron does not have these 2 little unbonded electrons. Unbonded electrons have a name. They're called lone pairs. 2 unbonded electrons equal 1 lone pair. So a lot of very similarities and some differences in the shapes. And now we can look and see, are they polar or non-polar? If they're symmetric atoms without lone pairs, they are non-polar because everything is balanced. You have an equal distribution of charge. So BH3 over here is non-polar. Hydrogen, 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 all the same outer atoms, symmetric, and no lone pairs. BF3, they are all the same outer atoms, so this is symmetric, no lone pairs, non-polar. NH3, he's symmetric, he has 3 hydrogens, but what is throwing off his symmetry? That lone pair at the top. If you see 1 to 2 lone pairs, he is polar, even if he's symmetric otherwise. This guy over here, he has 2 things that are making him polar. Fluorine and hydrogen, different outer atoms, so he's not symmetric in what his atoms are, and a lone pair. You only need 1. If you're asymmetric or different outer atoms or 1 to 2 lone pairs, you're automatically unequal and are polar. All right, how about these guys? Silicon dioxide. Silicon's going to go in the center, oxygen's going to go on the outside. Silicon, group 14, 4 valence electrons. This is something really close to a building block like carbon because he can do 4 bonds. Oxygen, group 16, 6 valence electrons, 2 gaps, so he can do 2 bonds. So the silicon is going to have a double bond with the left, and a silicon is going to have a double bond with the right. So silicon meets its 4 bonds, and the oxygen also meets its 2 bonds. Let's double check we're not messing up our valence. 1, 2, 3, 4. Silicon has 4 valence. Oxygen, on the other hand, is only showing how many valence? 1, 2. He should have 6. So this would be the completed structure. In real life, we wouldn't leave the dumbbells on the silicon dioxide, so we would write it like this, okay? Or you could also see it with dots. Sometimes the SOL does not show the bonds are clear, but sometimes they want to help you out with your counting so you don't make a mistake, and they'll show it like this. This is 4 electrons or 2 pairs. So it is a double bond. So that's the other way that you could see it shown. Silicon, there's 1 silicon and 2 oxygens in the structure. So if we want to find the total valence electrons, silicon has 4 valence electrons, oxygen has 6. So we should have 16 valence electrons, 16 electrons in the outer layer. Okay. 4, 8, 12, 14, can I just not add? 4, 8, 10, 12, 14, 16. I just can't add. So we do have 16. So your checks are checking valence, checking octet, and you can also check the total number of valence electrons. So let's bring him back to what he's going to look like as an actual structure so that we have it when we're comparing later. 4 electrons, unbonded on oxygen on each side, no unbonded electrons on silicon. OF2, oxygen in the center, fluorine on the outside. Fluorine, 7 valence electrons because it's group 17, so it wants only 1 bond. So the oxygen bonds with each fluorine. This is not a double bond. Oxygen has 2 single bonds, 1 with each fluorine. Oxygen wants 2 bonds, and he still has 2 bonds. When it's together like this, that's a double bond because it's 4 electrons between the 2 atoms. Over here, we only have 2 electrons on the left and 2 electrons on the right. So 2 single bonds making our 4 electrons. Oxygen is supposed to have 6 valence electrons. How many are here? Only 2. So we need to add 1, 2, 3, 4. Now oxygen has the proper valence electrons. Check every time or you're going to miss your lone pairs. Fluorine has 1, but he's supposed to have 7. So I'm going to add 6 more. So if you check this down here, 1 oxygen and 2 fluorines, to get your total valence electrons, 1 times 6 plus 2 times 7 is 20 valence electrons. Then you won't get lost here because you count up all these and you come up with 20. And then you can submit it just showing it like this. Again, you can use different colors. You can use X's and dots, or you can just make all the dots the same thing. Carbon dioxide. Carbon goes in the center, oxygen the outside. carbon and oxygen. Oxygen wants 2 bonds. Oxygen wants 2 bonds. Carbon wants 4 bonds. Carbon wants 4 valence electrons. He has 4. 1, 2, 3, 4. And then he's going to share 5, 6, 7, 8. So he completes his octet. Oxygen has 2 valence electrons, but he wants 6. So I'm going to add 4 more. Oxygen has 6 valence plus the 2 to make his gap for 8. That is how you get those octet. Everyone pretty much wants 8 electrons. That is your valence plus your shared electrons. Covalent molecules have sharing bonds. All of these guys are covalently bonded. If not, you can't draw it like this because ionics gain and lose electrons. Who doesn't follow the octet? Hydrogen maxes at 2. Boron maxes at 6. All right, carbon monoxide. So in this one, we only have 2. That one's going to cause us some problems. Carbon wants how many? 4. 4 is not stable. So he has to make do with 3. Oxygen only wants 2, but has to make do with 3. So sometimes we break all sorts of rules to make sure we're meeting our valence and our octet. Carbon here only has 3 shown, and he wants 4. Oxygen over here has 3 shown, but he wants 1, 2, 3, or a total of 6. But now when I check these things out, 6 plus 3 is 9. 4 plus 3 is 7. So in very interesting situations, the electrons can move around. So his final structure looks like this. You do not need to know him for the SOL because he does not follow the rules. But I did want to show you in here that things can bond looking identical to others. Silicon dioxide's Lewis structure is identical to carbon dioxide's structure. In fact, we could just erase the carbon there and put in the silicon. Why? Carbon and silicon are both group 14. So they are going to share in the same ratios if they have the same chemical formula. Okay? Carbon monoxide and carbon dioxide look totally different because they have a different structure and a different arrangement. That is okay. Oxygen doesn't have to be on the outside. In this case, he's the least electronegative, so he's in the center. So there's only so many variations of that. OF2, guess what? We could re-erase all the F's and put OCl2, and we would have the same exact structure because fluorine and chlorine are all group 17. We could take out this guy and put bromine. Heck, we could take out oxygen and put in sulfur because oxygen and sulfur are all group 16. So those things all work the same way. So there's really only so many structures that you can have. And then you can decide the polarity. If silicon dioxide is a particular polarity, then carbon dioxide is going to be that same polarity. Symmetric, same outer atoms, no lone pairs, non-polar. OF2 or SBr2 has lone pairs, so it's polar. Carbon dioxide, symmetric and no lone pairs, non-polar. Carbon monoxide, oh, he does not follow the rules yet again because there's only 2 of him. So you can look at him and go, oh, he looks kind of equal. But when you have only 2, you've got to do the change in electronegativity. So carbon's electronegativity is 2.6. Oxygen's electronegativity is 3.4. You subtract them and find the absolute value. So even in this case, when you subtract, you get negative 0.4. but you take the absolute value and, or sorry, you get negative 0.8. And then you take the absolute value and that gives you 0.8. 0.8 is greater than 0.4, so it is polar. So even though these guys look like they have a really balanced charge, in reality with lab experiments, we know that they do not. So when you only have two, you subtract the electronegativities. All right, so the electronegativities of all these guys are going to be 0 because hydrogen, no matter what its electronegativity is, minus itself, is always going to be 0. So your diatomics always are nonpolar because they have a balanced charge. Drawing these, there's only two. 2 points make a line. Hydrogen likes the single bond. That guy's done. Okay, he has 1 electron from each side or 2 total. So you could also draw him like this. Okay, that is the 1 electron on the left hydrogen. Here's the electron on the right hydrogen. They have 1 and they're sharing 1 and they max at 2 for their incomplete octet. Chlorine gas. Okay, chlorines. Chlorine, 7 valence electrons, 1 gap, so 1 bond. But make sure you show all these 7 valence electrons. 6 on unbonded plus 1 bonded gives you your 7 valence electrons. Same for both sides. And then they have an octet of 8. 7 valence plus 1 that they're sharing from the other guy. O2, oxygen likes a double bond. Why? Because he is group 16. So he has 6 valence electrons. He has 2 gaps. So he wants 2 bonds. He can't bond with somebody else. So he's going to do 2 bonds with himself. The oxygen on the left has 2 valence electrons. So he needs 4 more. The oxygen on the right, 2 valence electrons. So he needs 4 more. Oxygen double bonds with itself in its diatomic. So the structure looks like this, or if you wanted to show that, a single bond is 2 electrons. So you could show it like that, or even better, show it with the proper valence. Okay. The left oxygen is the red one. It has 6 valence electrons, and it has 2 more for 8. That is the completed structure of oxygen gas. Diatomic. All the Brinkelhoffs are going to be in one of these setups, single, double, or triple. Who are my Brinkelhoffs? Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Okay, how do we know which ones are which? Bromine, iodine, chlorine, and fluorine are all halogens. So all of the halogens are going to look like this. We drew the oxygen and the hydrogen. The only other one is the nitrogen. Nitrogen, 5 valence electrons because he's group 15. So to get to 8, he needs 3 bonds or a triple bond. 3 valence electrons on the left. So I'm going to add 2 more. 3 valence electrons on the right. So I'm going to add 2 more. That is my structure of nitrogen. All of these are nonpolar. What else do I know? They're all sharing bonds. These bars indicate that they are sharing electrons. So we are not making ions, no ions here. They're sharing. Sharing is caring. They're all nonmetals. They do not have electron transfer. Ionics, you would be physically moving the electron to the other side. And we only did that in that one weird instance. There are a million exceptions in chemistry. For year 1, you don't need to know most of the exceptions, so that will help you out. And that's all. Have a good day.